This will be the last lecture. No, the last on-site lecture, right? Because next Monday, that's a holiday, right? We will have class, but I probably do the video clips and you can watch it at your leisure time. All right. And the week after, that will be Songkran Day, another holiday. And the following, the 20th, would be the last milestone already, milestone 4. So, and after that, that will be final exam week. So, today would be the last on-site lecture. Oh, and will be the hardest one as well. Well, the most difficult part of the content to score on the final exam. So, please be aware and maybe like pay attention. Okay. All right. So today we will continue on from last time that we started talking about indexing and how important it is. Right. Last time we talked a little bit about the alternative 1, 2, 3, and things like that. But if we look at how we could classify index, or depending on what point of view you're looking at, we can look at whether or not it's primary or secondary. Like if the search key, remember the search key, like let's say if you want to sort something based on authors would be the search key. If you want to search on ISBN or keywords or whatever, those would be your search key. And if the search key contains the primary key, we just call it primary index. That's it. Very simple and straightforward. If the search key contains primary key, primary index. Everything else, we call it secondary index. That's it. Okay. But sometimes in some tables, we may have candidate keys. And the candidate keys are unique keys, right? So if you want to emphasize that our search key contains candidate key, we can call it unique index as well. But usually, if you just want to classify whether or not it's primary or non-primary, we can just say primary index or secondary index. Okay, this is one way of looking at index. Okay, another way, which is in separate ways to look at it. We can look at it as clustered index or unclustered index. Okay, clustered index is easy. If the order of data records, the real records, versus the order of the index itself have similar ordering, we call it clustered index. Otherwise, we call it unclustered index. So if you go back to alternative 1 from last time, remember alternative 1 is we use the raw data as the index structure. So of course, the order of the index and order of the actual data would be exactly the same, right? So basically, alternative 1 automatically implies clustered index, right? And usually, the one database can be clustered and at most one search key. Well, roughly speaking, but sometimes we may have similar search keys that has exactly the same ordering as others. So that could also be the case that is also clustered on others, like automatically because of the nature of data itself. But usually we can deliberately sort on one thing. So that one thing would be clustered on that search key. Okay. Now, for example, if you have primary index, what side effect you would see? So let's say we have data on data pages and the data are sorted in some way. And if the index, this is the index that you created, and let's say the ordering of the index goes like 5, 13, 14, 16, 18, whatever. And it happens that 5 or something smaller happens in this data page. And then it keeps on going in the same ordering as the primary index. We just call it primary index because it has the same ordering or something close to. But if you have secondary index, the order of the index and the data itself are not in the same order. So when we look at the pointers, they will just be like go back and forth between pages. So that's typically what happens in secondary index. Okay. And another thing that would happen afterwards, if you decide to have secondary index, it must be dense. We'll look at what dense means in just a little bit. Okay. And every time the file or the data is modified, all the index must be updated. Okay. Yeah, we learned about the B+3 index last time, that whenever you have insertion, deletion, whatever, we have to update the index accordingly. Okay. And if we want to do sequential scan using primary index, it's very efficient because if you want to list out every single thing in the database out, and if it's the same ordering as the index, well, in terms of proximity, like how close they are on the next record, that will be in the same block, in the same page. So that's very efficient. But if you want to use an index, sometimes it's too expensive, or sometimes worse than having no index at all. Okay, you see a little bit in the later part when you have to do the calculation. Okay, and then you probably understand it better. Okay, here's an example of figure index. Let's say we have the account table. We have some account number. We have the name of the city. And then this is the account balance. Okay. So let's say if we want to create index based on this field, which is the balance field. All right. So what we need to do is we need to take this column and then we sort. Okay. So you could see that this is the index part that we created. Sort based on the account balance. To start from 400, 500, 607, 750, and 900. When we have duplicates, we only display it once. Okay. But if you look here, second index must be dense. Dense means that, let's say in the case where we have 700, so you see that we have 700 here, here, and here. Okay. Dense means that we must have the pointers from that search key to every single data records. Otherwise, you will lose the item. Here, when you want to find items with balance 700, so you go to the index entry here, 700, and then you follow the pointer. So the first one, this one, here's the second one, and here's the third one. This is called dense. We have all the pointers needed to point to every single data records available. Okay. And if there is only one single item, that's not a problem. Let's say you go 400, 400, just go there. And that's, now you know that there's only one entry for 400. If there are more than one, there must be listed there, and there must be a pointers points to every single one of them. Okay, so this is called dense. And it is required that all the secondary index must be dense. Otherwise, we will not be able to find the item fast. Okay. Now, clustered versus unclustered index. Let's say if it's clustered, this is the, let's say it's real data record. That means the ordering of the data just go on as usual as what the raw data is, but the data entries, these are the index stuff that you created by itself. And then if you look at the order of the data entries that points to the actual data records, they're following the same order. So if you look at the pointers, there will not be pointers that cross each other because the order just go on in the same direction or in the same ordering. But if it's unclustered, let's say you have the same data records. So you have the same ordering, the same thing. But the data entries may be sorted based on search keys, other fields. So of course, there would be typical that the entries of this one could point there, the other one could point to others, and they just cross each other back and forth because they don't have ordering. All right, so that's what unclustered and clustered index would sort of look like. So you could imagine that if it's unclustered, and if you have to access data pages in like go to page 1, page 10, page 2, page 5, page 1 again, things like that. So you have to spend a lot of time reading different pages over and over. Versus if it's clustered index, you just read the page one by one in order and one page at a time. And usually we don't have to reread the same page. So that would make things faster. So if possible, if you want something to go the fastest, clustered index would be the best choice. Okay. But since there is only one search key that it could be clustered on, so you have to think carefully which one you would like it to be clustered and which one would be unclustered. Okay. Okay, so for dense index, well, like I said earlier, that if it's dense, the index record must appear for every single search key value in the file. So in the previous ones here, so when we look at this field, you have to think about, how many unique values are there? So here, if we count, there will be 7 unique values, which are all these values. So we must use all of them to create index. Okay. So here we have we have Brighton, we have 2 downtowns, we have 1 Ninus, we have Perry Ridge, and we have 1 Redwood and 1 Round Hill. So 1, 2, 3, 4, 5, 6. We have 6 different search keys. So we need to use all of them to create the index, and we call that dense index. And if it is, if all the records are stored in block like this, well, it's probably enough to have one pointer that points to the beginning of the page blocks, and then the next one, it follows that. Okay, that's the same ordering there. But the idea is that at least for the search key, we need to have every single item, like for all the unique search key values. Okay. But if it's sparse index, we can select only some search values. Yes. Yes. Clustered and unclustered, we just look at how things are ordered. Let's say if this is the your data, and this is your index. In this particular case, we will call it cluster index as well, right? Because the index ordering and data records ordering has the same order. So this is cluster. But here we just want to look at how dense index would look like. So we need to have all the unique search key values to create a dense index. Okay. Secondary index usually unclustered. Yes. Clustered here. In the unclustered class, yeah. Okay. Yes. These are things that you created by yourself. So you look at your data records and then you decide which attributes you want to make the search key on, and then you create those. The arrows are the pointers that points to the actual data records. So just like if you go to the library and then you have the link, like you want to search based on the authors, you want to search based on the keywords, ISBN, whatever. These are usually they're all secondary index in the library. So it would be this part. And then each one will point to different part of the library, like all the shelves and everything, which will not be the same order as the index order. Yeah, so yeah, they're all secondary index. Okay, so for sparse index, since we only need to use some of the search key values, well, of course, it would take less space and less maintenance because the index entry would be smaller, but it will be a little bit slower than dense index because one pointer will contribute to many data records. So you probably have to do a little searching within that blocks, that part. Okay. So there's a little trade-off that if you want to like save space on creating index, sparse index would be one choice that you could do. Okay. Here's an example of sparse index. So here, instead of having all the unique values or search key to build an index, you just select some. So here, just pick Brighton, Minus, and Redwood. So Brighton itself could contribute to this block of data. The Minus would be here, and Redwood would be there. But the thing is, if it is not clustered, it would not be cool to do sparse index. You cannot do that because if we could do sparse here because we know that if we want to find downtown, we know that downtown is between Brighton and Minus. So we just go to Brighton and then we search it down and finally we get to see downtown. But if they're not in this order, you would not be able to find downtown quickly unless you do sequential scan eventually, right? So it must be sorted first. Otherwise, you cannot use sparse index. That's why we say that if it's second index, it must be dense. Because if it's sparse, well, you would not be able to find all the data records fast. Okay, now let's come back to this one. Remember last time we talked about like alternative 1, 2, 3, whatever. But now, table of content in terms of cluster and unclustered. Do you think this is clustered or unclustered? Index. So this is called index because we created the table of content after we have the raw data, like the whole textbook content. Okay, you think this is clustered or unclustered? Clustered, right? Very easily because, well, if you look at the page number, we start from page 1, well, 1625, and then it keeps on growing in increasing, non-decreasing order. Okay, keep on going. So if you map this to the actual content of the textbook, we'll just go in the same ordering or it's like similar order. Sometimes we can't say it's exact ordering. Sometimes it's swapped a little bit, but maybe it's in the same data page, so it doesn't really matter much. So as long as it's in the similar order, we call it cluster index. This is cluster index. Now, what about this one? Is it clustered or unclustered? So this one is sorted based on the keywords, right? So you could see that, let's say you look at merge sort. So even though this is in increasing order, 367, 370, 378, 5, but still, this one and this one and this one, the ordering of the items in the index part versus the ordering in the actual textbook are different order, right? So they're not the same order, so we call it unclustered. Right. We just look at how they order in terms of the index ordering and the actual data ordering. They're not obviously not in the same ordering, so we call it unclustered. What about primary or secondary? Is this secondary or primary index? Well, we would. Okay, this is unclustered index, and it's also secondary index. Okay. Now, if we want to look at, well, since eventually today we will do the cost calculation, so we have to think about how data structure of the index works and how we organize the data entries in index. We have hash index that we talked last time. We have B plus tree index, right? We have tree base and hash base. And we also have to look at how the data is organized. So if the data is unsorted, we call it heap files. We talked about the word heap last time, that it's not the same heap that you did in the data structure class. Heap file is just the unsorted file. That's all. So whenever you want to add something to your data page, let's say the OS and the file system will keep track of all the data pages. If data page is full, well, it's a full page, and then its responsibility to look for the next free space, the next page with free space for you. So next time when you want to insert something, it will bring up the next free page that you can put the data in. You just append to it. You don't need to sort, don't need to do anything. Just keep appending, and we call that heap file. Okay, so one thing is heap files are unsorted. Okay, the next structure would be sorted file. In sorted file, we just have to sort everything in the data page right here. Okay, sort from smaller to larger, larger to smaller, doesn't really matter as long as it's sorted in some way. Okay, if it is sorted, we can find things faster, right? You can use some binary search tree or whatever binary search to search for something in the data page that are sorted faster. Or sometimes, well, if you only have sorted files only with no indexing scheme, we still gonna get things get searched faster already because of the search structure that you could do. But you can also put extra index structure on top of sorted files. Well, that's part of the B plus tree that we talked about last time. That say we have the B plus tree, on top of the sorted file. So down here, this is sorted order. And then we can build a tree on top of it. And of course, we can search for things fast. But it will be faster than binary tree because usually for B plus tree, we have larger nodes, much, much larger nodes. So the height of the tree will be really small, usually like height 1 or 2, that's it. And then we can get to our leaf node really quickly. Okay, so for tree-based indexing, it has to work with the sorted order file, but not necessary. We will see later that we can also put B plus tree on top of unsorted order file as well. Okay. So this is for sorted file without index, only this part. It will be fast because we can use binary search for it. We can also have indexing structure on top of sorted files as well. That would make things faster. And also we can put the index structure on top of unordered files. Okay, we'll take a look at that in just a little bit. But okay, another one is hash-based indexing. We have data page, but now the data in data pages will not be sorted based on the typical sorted orders that you do. Usually, like let's say numbers from smaller to larger like that, but it's based on hash function that you hash into. Okay. So whatever the hash function says the data would belong to, we'll just go to that page. So if you look at the items in the data page itself, it's not going to be in the typical sorted order. Yeah, but it will be in buckets of the same bucket will contribute to the same hash value from the hash function. Good thing about hash function will be it will be fast, really fast to get the hash value. Okay, for hash-based indices, we already talked a little bit last time that we would hash on search key, but the same way as tree-based indexing. You can hash based on the authors, you can hash on age, you can hash on like account balance, anything the same way. But the hash function would tell you which data page this value of the data should belong to. And then just go to buckets or data page. Okay, and the bucket, depending on different types of hashing schemes you use, if it's like static hashing, or you will have like overflow page or overflow buckets. But if it's some other type of hashing schemes, or if it's extendable hashing, we will not have overflow bucket. If it's linear hashing, we may have some overflow, whatever. So those are like the details, but the basic idea is we have buckets of data that hash function will quickly get you the hash value and you can locate the data fast. Okay. And we know that it's good for equality selection only. It's totally bad for range search because things in the bucket are not sorted in the typical way. Like the adjacent values would not be usually not in the same bucket. Now we have to know how to handle updates in the search. But we already talked about how that mechanism works last time already, right? But for hash index, we can use alternative 1, alternative 2, 3, doesn't really matter. We can also use alternative 1 for hash also if you want. So that means instead of having secret index, just a search key in the bucket, we can use the whole data records in the bucket. Well, that's alternative 1. That's the only difference, right? If it's not alternative 1, all we need to do is we just pick the search key that we want, and we only put the search key in. Yeah. Well, here's an example of, let's see, if this is the original file, data records that has the name, age, and salary there. Okay, and then we have buckets, different buckets. Let's say here we do alternative 1. This is alternative 1. Why is it called alternative 1? That's because we use the whole data records to put into the bucket. Okay, so what we need to do if you want to hash on age. So if you want to put like 44, you put 44 in here, and the hash function h1 would say age 44 would be in this bucket. And all you need to do is just to put the whole data records of age 44 in there. And if you want to search on it, if you want to search on age 50, you put 50 in there, and then hash function would say, okay, go to bucket number 3, and so on. Okay, it will tell you which bucket to go to. And then if you want to hash on other search key, so here age will be the what is it? It's clustered based on what? Well, is it clustered? Not really clustered. Well, if you want to hash on salary, this is secondary index. So here, instead of using the whole data record, we just pick only this field, the salary. And then when we put salary in there, let's say 3,000, and it would tell you which bucket it belongs to. So in this bucket, it will contain all the salary whose hash function has the same value. So you could see that 3,000, 5,000, and in this bucket, 4,000, 2,000, 6,000. They're not in the typical order that similar to B+3 or whatever that you ordered, because it's not populated based on those ordering. It's based on the hash function. Okay, somehow it turns out that the hash function gives them the same values. But all of these have the same hash values. All of these have the same hash values. Okay, here's another example of hash-based indexing. Well, we have different buckets here. We have bucket 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So a total of 10 buckets. And each bucket, so if you see here, you see that this is just a search key, secondary index, right? So when we want to look for 13646, we just put that into the hash function. Hash function would say, oh, bucket 0. So you go to bucket 0, and then you follow the pointer, and then it will point you to the actual data records. And we can do it fast. But if you want to do range search, that would be horrible. It would be difficult. Because let's say the next value of 13647, definitely, usually it would not be in the same bucket 0. It probably be in other buckets. And then you have to read another page or another bucket up, and then it will cost you more. So range search is bad. All right. Now, here's the things that you have to start to really pay attention on, because we will start doing the cost model analysis. Okay. We would ignore all the CPU costs because we know that CPU cost is really fast comparing with the IO, right? So all the page IOs would subsume everything. So just to make it simple for you, we just look at page IOs. That's it. That's good enough. Okay. Right now we have only 3 values to worry about. Okay. We have B, which is the number of data pages. Okay. This is another way of telling how large your files would be. Okay. Because all the data records will be put into the data pages. And see how many pages. If this file contains 100 pages, the other one contains 1,000 pages. So obviously 1,000 pages will be bigger. So we will look at how many data pages we have. That's in terms of B. And in R is the number of maximum data records per page. This is how big the page will be. If the page could contain 10 data records or 100 data records, that's what R is about. Number of maximum data records allowed. And maximum, okay? We don't care how many we have at this point, but R is the maximum allowed. Okay, it's the size of the page. That's basically what it is. And then another one is D, is average time to read a page or to write a page. Just to make things simple, we just make it the same thing. Okay, and our goal is to measure number of page IOs to do different operations of the typical things. We have scan, we have insert, delete, whatever. Okay, we would ignore the prefetching or anything that OS could do for you. Because sometimes the OS is like intelligent enough that, oh, I know that you will be calling, reading this page and this page. So I'm on this page right now. Just take all 5 pages there because I know that you will use it later. That's called prefetch. Okay, we will not do that because otherwise the cost analysis would be really complex. So we just count whenever we need it, we just grab it from this. No prefetching is allowed. Okay, and we would do average case analysis. Even though we could do best case, we could do worst case, but yeah, we'll look at average case analysis. And we'll try to simplify things as like just to make sure that you understand how each data model or index would affect the cost. And here are the operations that we need to compare. The scan meaning you have to list out all the data records. We do equality search. We do range search. We do insert one data record only. We do one deletion of one data record only. Okay, we need to be able to compare how expensive they are on each operation based on different type of index schemes that we use. Okay, and file organization, we have 5 variations. The first one is a heap file, but we know that heap file is unordered file. Whenever we try to insert something, we insert at EOF. What is EOF? End of file. Okay, we insert at the end, appending at the end. The second organization is sorted file. Okay, in sorted files, we assume that there is no index available. Just make sure that your file is sorted at all times. And let's say we assume that it's sorted based on ToSearch key, it's a composite key. So sort based on age first. And if we have the same age, we sort based on salary. Okay, so this is how we would make assumption on our analysis. A sorted file, no index, but we sort based on age and then salary. The next one is clustered B plus tree on search key, alternative 1. Okay, first, alternative 1 means that we take all the data records, like with all the fields, everything, and then we sort based on some search key. Okay, and then we have clustered B plus tree index on top. So it would be clustered, of course, because the order of the index of the B plus tree and order of the data records will be the same. Okay, since it's positive. It's clustered. Next two variation will be unclustered because we only have one option for cluster. The rest must be unclustered. Okay, now we have heap files. Why heap file? Because we cannot have clustered index anymore. So the rest, the order of the files and order of the index will not be the same ordering in. Okay, so that's fine. Well, the data records order and the B plus tree index order are not the same. So that's called unclustered B plus tree. And we'll see how it will affect the cost on those operations. And then the last one, we heap file the same, like with the different ordering, and then we have hash index on top. Okay. So now we have 5 different file organization. We have 5 different operations to look at. Okay. To make things easier, we do a little bit assumptions. For heap files, when we do equality selection, we do it on the key. Key and exactly one match only. So let's say if you want to search for someone with age 15, once we find the first person with age 15, we stop. And then we look at the cost. Because otherwise, if we have to find every single person with age 15, that would be different costs because we probably have to do the whole search, the whole sequential scan. Okay, so that's going to be different costs. Okay, exactly one match, and then we stop. For sorted files, we make sure that we have to compact the file after deletion. What does it mean? Well, you go back to like the simple array, where we have array of data, and then we delete something out of the array. We have a hole in the array. Now, that's in sorted files, we have sorted ordered items, and then we delete something out. We have a hole in there. We would not allow the hole. We have to compact the file afterwards. But that's what we have to do for sorted file. Okay. After deletion, we have to move everything over so there's no empty spot. For index, alternate 2 and 3, we won't talk to alternate 1 because that's already the third organization we talked about. For alternate 2 and 3, data entry size assumption will be 10% size of data record. Why? Because for alternate 2 and 3, we only pick search keys. Let's say in the full data records, there are 10 fields, 10 attributes. Well, we just pick some as a search key. For example, we just pick authors. We just pick keywords. We just pick ISBN as a search key. So to build up the index structure, that will be smaller, much smaller size comparing to the full data records. Right? So we assume that the size of the index is 10% of the full size. Okay. And again, if you forget already, data entry is not the data. Data entry is index part. Okay. If you don't remember, well, it's in the previous lecture. Like data entry means index entry. Okay. For hash, we assume that there is no overflow buckets. Okay. Just to make your data analysis easier. And if we would not allow overflow, if all the pages are already full or all the buckets are full, we will not be able to insert things into buckets unless you do split buckets and all, right? So to make things easier for you, and this is a typical in typical DBMS, that the DBMS will not have initially put everything in a full page. It will leave some empty space for future insertion. So this is what it is. Let's say we allow it to have initially 80% page occupancy. So instead of putting everything in full page, I allow only 80%. And then we have 20% left for future insertion. Okay. That's for hash. Now, if you think about, let's say in the beginning, we have 100 data records, and then I have 10 pages. For each page, I allow 10 items. Okay, how many? Well, for each page, I have 10 items, 10 items. So I have 10 pages, and then I can put everything there, 10 pages. But now, if I only allow 80%, so each page I can only put 8 items in there. So 10 pages would not be enough, right? If I have 10 pages, I can only accommodate 80 data records. So how many pages do I need? How many? Instead of 10 pages, I would probably need 12.5 pages or 13 pages so that I could put 100 data records in there. Right. Again, you need to understand this really well. Otherwise, it will be difficult later on. Okay. Starting with, we have capacity for each page. Let's say I have 10, allow 10 items to put in a page. I have 100 data records. So I can put 10 data records in one page and it's full and then keep on going. So 400 data records, I will need 10 pages full. Everything is full, 10, 10, 10, 10, 10. So 100 data records, I have 10 full pages. Okay, that's for 100% occupancy. Got it? Okay, now, if I only allow 80% to be filled in a page, I cannot put 10 in a page anymore. I can only put 8. So 10 pages will not be enough for me to put 100 data records in, right? So you need to be able to find out how many pages do you need to be able to put 100 items in there. How do you do that? Well, easy. So if you're going to do the calculation, I only allowed 80%, right? But originally, if I have B pages, I want to know how many pages or how many X pages do I need? So that would be 100B divided by 80. That would be 1.25 B pages. Okay, so originally, if I have 10 pages to accommodate everybody, but if I only allowed 80% occupancy, I would need 1.25 B pages or 12.5 pages to put all 100 data records in there. But we cannot say 12.5 pages because we have to go with the full page, so 13 pages. Yes. Can you say it louder? Yes. See you, usually the DBMS will have a default value for you, but if you want, you can actually like tweak in and then you said, oh, for this actual database, it is really dynamic. So you expect to have future insertion a lot. So you would reduce down the occupancy to make it like more vacant for future insertion. Yes. So usually if it's database that do not have a lot of insertion, you can increase the page occupancy to reduce down the number of buckets. Okay. But usually it will have some default value for you, but it's not 100% sure. And the same way with the tree. For B plus tree, it also has something very similar. That in a page, we will not make it a full page because otherwise when the page is full, we have to do a split page and then on the B plus tree, we have to like do something to make it B plus tree all the time. Okay. So let's say for tree in here, we make assumption that it has 67% occupancy or 2/3. Okay. So if we want to figure out the file size, if we allowed only 67% or 2/3 full, so for 2/3, if we originally have B pages to take care of, how many pages total we need to have? So that 3B over 2, that's 1.5 B pages. So if we want, if we have 100 data records total, and then we allow data records to put in a page for only 2/3 full, so eventually you need 15 pages to fill in all the 100 data records. Okay, and again, all of these are user defined, so you can change the occupancy rate to whatever, and you should be able to do the calculation accordingly. Okay, so in the exam, you will be given different occupancy rates, so you should be able to do the calculation. All right. Okay, now ready. We start with the first one, which is the easiest of all. Okay, heap file. Heap file is the unordered or random order file. Okay, so when we want to scan something, okay, we do all the scan. That means all the data pages must be scanned. Okay, remember we have B, we have R, we have D. B is number of total pages that we need to put all the data in. We have D is the time it takes to read or to write a page. And R is the size of the page, like the maximum number of data records allowed in a page. Okay, for scanning, we don't care about R because we have to take the whole page. We have to read the whole page anyway, because we have to retrieve every single item there. So if we have B pages total for scanning, we will need to read all B pages. Each page would take D time. So scanning would take B times D. Okay, very simple. Okay, next, equality search. Remember, everything is unsorted. If we want to find some value there, average case analysis. Remember last time when I had the example, like all the last name, like 22 rows there, if it's sorted versus unsorted, right? For unsorted file, well, average case, the best case would be the first one, right? The worst case would be the last item. The average case would be somewhere in the middle, right? So if you have B pages total, average case would be you would find that particular item halfway through, which is 0.5 B pages, right? So if you have total B pages, so on average, you would get to your answer in 0.5 B pages. And each page would take you D time. So overall, that's 0.5 B times D. That's for equality search. Now the range search, that's also easy. If I want to find like all the people with age 15 to 20, and it is unsorted, so you have no other choices. You don't know where 15 will be located in your unsorted file. So eventually you have to do the scanning, the whole scan, and then you look for 15, 16, 17, 18, 19, 20 along the way. So overall, for range search, it would take you just like the whole scanning, right? Because it's unsorted. You don't know where it's located, so you have to scan for the whole file anyway. All right? Yes. Range search. For example, I said, I want to look for a person with age 15 to 20. And all the ages are scattered in a file, right, in different pages. So if I want to find 15, 16, 17, 18, 19, 20. Well, there is no way that I could target to any particular page. And it's not like quality search that I can go halfway and then I find my thing, right? So I have to go from the beginning and then look for 15, 16, 17, 18, 19, 20. Is there anything in there? If not, just keep on going. Eventually, you have to read every single page. Yeah. Just to make sure that you get everything. Okay. Now for insertion. All right. Now, for insertion. What do we have to do to insert? Well, everything is in unsorted order, and we insert at EOF, at end of file. So what it does, the OS can bring the last page that has a free space for you to put in. Right? So that's the cost of fetching. You have to fetch the last page that has an empty spot, not empty page, but it could be something in there, but it has some empty spot there for you to put the insertion record in. Okay, so that's one page to read. And that one page costs you D time. That's one page to read. And then you have to, when you read it onto main memory. And then you add a data record. When you add it on main memory. Okay, you put it in the page there. And then if you're done and then you leave it there, your database will not be updated, right? So you have to write back that page that you just modified. So write back would take you another D time. So one read the current page onto main memory, and then you update by adding one new data record there. And then you have to write that page back onto database, onto disk, so that the chain will be permanent. All right. So one read, one write. So total, that's 2D. All right. Next one, delete. Now, delete is different because for insertion, you always insert at the end of file, right? You always bring out the last page and then do insert. But to delete, you have to search for things to delete, right? I want to delete this person's name. So I have to search and look for that person's name. And I have to take that page onto main memory and then I do the deletion. Okay, so first thing, I have to locate the record to delete. How much time do I need to locate the data record to delete? Well, that would be equality search, right? I don't know where it is. It could be a base case, that would be the first record there, or it could be worst case, the last record there, but on average, because this is average case analysis. So on average, my record to delete is somewhere in the middle. Okay, so it would take 0.5 BD there to locate the record to delete. And in that case, it will bring up the page that I want onto main memory. And then I could remove or delete the data record from the page. Okay, but this is on main memory only. So I have to write back. Modify page to this. So write back, take another D time. Okay, so for deletion, let's say this is a quality search. Quality search, that would take 0.5 BD plus D. Any questions about this heap file operation? This is the easiest one of all. Okay. Question? No question. Okay. So this is 5 slots out of 25 that we have to do today. All right. Okay, the first rows, that's for heap file. Now we go to the second row. This is a sorted file with no index. Okay, think about sorted order files in data pages. Now, if you want to scan, that means, doesn't matter if it's sorted or unsorted, not really, because we have to list out every single item in all the pages anyway. So eventually you have to scan every pages that we have, every page, right? So we have B pages total. So that's all we need to read. So that's BD, the same way as the heap file scan, because there is no other way without looking at every page. Okay. All right, so that's B times D for scanning. Now for equality, that should be better comparing with the heap file version, right? Because it is in sorted order. So of course, when we want to look for things, it should be faster, right? So to locate the record, how much time do I need? If there is no index structure, right? I have sorted files, and then I can use binary search, right? Binary search. If I have B pages total, and I want to look for page 15 there, well, number of pages would not be B pages. It will be log time, right? This. To locate the record, it would take you log B base 2. Right? That's the amount of pages that you may need to access. This is for worst case, also with average case. Right. Okay. So this is how many pages you need. So times B. All right. Now for range search. For range search, let's say I want to look for age 15 to 20. I will have to search for the first item. Okay. Search for first item. So search for first item will be the same as equality search, right? So if I want 15 to 20, I have to look for 15 first. Okay, but search for first item, that would be D log B base 2. Okay, that I would get the first item. But once I know the starting point, I would know the rest, right? Because everything is sorted, so I can scoop out all the items afterwards until I see 20 and then I stop, right? Yes. Okay. But how many pages do I need to read? Well, it depends, right? It depends on how many matches do I see, right? So if, let's say, all the age 15 to 20 is contained in one same page, I don't need to add extra time. But if it spill over to the next 2 pages, so I need to read 2 extra pages there. If it spill over to 10 next pages, I have to read 10 extra pages. So it depends on how many match items are there in a page, right? Not match records, match page. Okay. If I need 2 extra pages, that's how many pages I need. And then multiply by D. Okay. So it's the cost of searching the first item plus number of pages that all my matches will fall into in terms of page. You count how many pages extra I need and then times D. That's for ring search. Okay. So actually, I just put it in short, but to make it actually correct, I have to say match pages times D to make it correct. Okay, now next for insertion. Think about if everything is in sorted order and I have to insert something in there, I have to make sure that I maintain the sorted order, right? So how do I do the insertion? First, I need to find a position to insert. First, find the position to insert. How much time do I need to find a position to insert? That will be the equality search, right? That would take me D log B leads to. Now I know where exactly to insert by having that page onto my main memory already. Okay. And that page is there, so I can add a new record. A new record. Okay. And then what? Well, if you peek into the solution, you see that it's search plus BD. What how in the world where BD comes from? Okay. Listen carefully and think about if we have full array, it's already full, you know where to insert, but there is no space, right? So you need to move things over to make a spot, and then you can do the insert, right? So it's not that easy that, oh, I find position insert and then I add a new record there, right? To add that new record, it takes some work, okay? And in average case, we will see that in average case, we will insert at the middle of the file of the data pages. Okay. Somehow. Okay. So let's say if we want to insert something in the middle of data pages, but everything is full at this point. So we need to make room for it. How do we make room for it? So I have to read the second half and then I move things over by one. Yes, from the last page. And then I move things over, move, and then I have one spot available, right? Yes. Can you do that? Yes, you can. Right? Think about array. Like we need to put something in the middle of the array, and then you have to move things over by one spot. So you have to move the last one over by one, keep on going. So that means the second half of the pages must be read. And then modify, move things over, right? And then once we have a spot available, you can add a new record in. And once you add a new record in, you have to write back all those pages back. Okay? So in the first half, we don't touch. We don't need to touch the first half. But we need to make sure that the second half got modified accordingly. Okay, so you have to fetch the second half of all the pages. Fetch it, and then move things over until we have one spot to add a new data record in. And then those pages, which are the second half of all the pages, we have to write them back and then okay. So here is what we have to do. We have to fetch and rewrite all of the second half of data pages. Okay. If we have B data pages total, so we have to read 0.5 B pages, the second half, read it in, fetch and read, and then modify everything and add data record and write back those pages, which are another 0.5 B pages. So to fetch, that takes you 0.5 BD. And to rewrite, that's another 0.5 BD page. So total, add them up, and then we get BD. Okay. So here, for insertion, we have D log B base 2 plus BD. Okay. But BD doesn't come from all the B pages. It's only second half of the B page. Read in the second half and write back those same second half. Okay. Any questions? Okay. And this is in average case. That's why we can assume that second half has to be modified. Okay. All right. So here, search, that's equality search. All right. Now, next one is deletion. Remember in the assumption page that when we delete, we have to compact the file after we delete. So first thing, we want to delete something, we have to search for data record to delete, right? Okay, to search for a record to delete, that takes equality search time, like the same way as to insert something. So D log B base 2. That's for the search. Now I search for a record to delete. So that page is up there. And then now I can remove a record. Now that's all the work that we need to do. Because if you remove the record and then you write back that page, the page will have a hole there, right? But in assumption, it says that you need to compact the file after deletion. So no hole is allowed. So we need to, well, put everything move over by 1 so that the empty spot is gone. So you do things in reverse as the insertion. So we assume that on average, the things that we want to delete is in the middle of the file. So again, we need to take care of the second half of the file. The same thing, we fetch and we have to rewrite. All second half of the pages. That means since we have one hole there, we have to read in all the second half of the pages and then we move the records over by 1. Move over. And then all those pages that got modified, we need to write back. So when we fetch only the second half. So that's 0.5 B times D time. And to rewrite, that's another 0.5 B times D. So overall, we have B times D. So eventually both insert and delete will take the same amount of time. So search there. BD. But you have to understand that BD from both cases are not about reading every single page speed. It's only second half of the page. Okay, any questions so far? The next one is cluster B plus tree. Alternative one. Okay, remember alternative one, it's that we take the whole data record with all the fields, everything together, and then we rearrange based on the search key that we want. Okay. Now, just a recap before we go on. It will be the left-hand side part. But if it's alternative one, the actual data records is here. And then we have the cluster index on top, cluster B plus tree index on top. Okay. So if you look at the order of the data entries and order of the data records, they're all going to be very similar, all the same. Okay. All right. For cluster index, if we want to scan everything, that means all the pages here must be read. Okay. But for all the index part, all the pages will have page occupancy of 67%. So here we have 67% occupancy. So instead of having B pages total, we would end up having 1.5 B pages. Right? Okay. From now on, if we talk about tree base with page occupancy of 67%, we know that now we need to use 1.5 B pages to take care of the same amount of data records. So now to scan everything, instead of scanning all B pages, I have to scan all 1.5 B pages. So that would be 1.5 B times B. Okay, because we need more pages to take care of. Okay. So that's for scanning. Now for equality search. Equality search, we have, well, it's very similar to sorted file, except that for sorted file, we use binary tree to search for things. But for this one, we use B plus tree. The big difference would be the fan out. Remember the fan out, the number of pointers per node. For binary tree, that's 2. That's why you have these 2 right there. So now, if we use B plus tree fan out, we use fan out F. Whatever F is, it could be 50, it could be 100, it could be 400, whatever. Okay. So here, number of pages will be log base F. But the number of pages will not be B anymore. It is 1.5 B. Okay. Times D. Okay. You could see that it follows something very similar to sorted file. The only differences are the first one is number of pages. It's not B page anymore. It's 1.5 B. The second one is a fan out. It's not 2 anymore because it's not binary tree. It's B plus tree, so fan out is F. Yeah. That's the only 2 differences. Okay. 1.5B. Okay, if you go back to in the assumption page that we talked about, occupancy rates of 80% for hash and 67% for tree. For this one, if it's 67% occupancy, well, how did we get 1.5? 67, that's 2/3, right? 2/3. And originally we have B pages to take care of. We want to find out if we only allow 2/3, how many pages do I need? So X would be 3B over 2. So that's 1.5B pages total. This is for 67% occupancy rate. But if it's 80%, that's for hash. So 80%, you do the same way. So X would be 100B over 80. So that's 1.25B. So that's for hash. Okay. So for now, with the assumption of 67% occupancy rate, we will deal with 1.5B page. And if we talk about 80% occupancy rate, we talk about 1.25B pages. But again, all these numbers are well user defined, so you can change it to others, and your calculation should also reflect those as well. Okay, so that's for equality search. Now for range search, if I want to find someone with age 15 to 20, again, so first, very similar to sorted files, you have to locate the first data record, the first record of 15, age 15. And to locate that, that's the equality search time. So that would be D times 1.5B. There. Okay. For that, I could locate the first data record. And then the rest, just like in the sorted files version, we need to add number of matched pages times D. Whatever pages or how many pages that we have in the extra matches, I have to multiply by D. If those ranges contained in the same page as 15, I don't need to add anymore. But if it needs one extra page, that's 1D that I have to add to. If I have 2 extra pages, I have to add 2D to it. So depending on how the matches fall into the extra pages. So here, that's the pages times D. All right. Now for insertion. Well, the sorted files version and clustered version are very similar in the idea of calculation. So if you want to insert something, you have to find the leaf page that you have to insert something into, right? And that could take you the equality search time. That's D time log of 1.5B base F. This would bring up the leaf page that you're supposed to insert the value into. Let's say I want to insert number 17 into my database. I will search for which data page should 17 belong to. So it's like equality search for 17. And then I will know which data page 17 should be in, right? So it will bring out that page. We assume that occupancy rates are like 67%, so it's not full. So we have enough space, enough room for insertion. So we can just add new data record. When we add new data record in, are we done? No, we're not done because we have to write back that page. But instead of having to like read all the second half of the page and things like, we don't have to do that anymore because now we have index structure to take care of. So all we need to do is we only modify that leaf page. We only need to write that leaf page back and then we're done. Okay. So write back the modified page. That's only one key. Okay. So we have the equality search here plus D time. That's to write that modified page that you just add the value in and then just write that page back. The index structure stay the same. We don't have to change anything, right? As long as that page has some room there, you just add the new value in and then everything else stay the same. So you don't need to do anything else. So for insertion, that's all we need to do. Now for deletion, well, the same idea. You need to find where the stuff that you want to delete is located. All right. So first you have to find the leaf page to delete a record. And that would take you the same equality search time. There. So if I want to delete the person with age 17 there, so I need to find out where that record is located. So it would take me equality search time to bring up that page onto min. And then I could remove that data record. Once I remove, I have to write back that modified page so that my deletion is permanent. So I have to write back the modified page. That's take me time. So you could see that insert and delete takes the same amount of time, right? So the same search, equality search there plus D. All right. Any questions so far? All right, we're about halfway done. These three roles are easy ones. Okay. Now the complex stuff is coming up in unclustered plot. We're gonna take a little break. Okay, just take a few minutes break, and then we come back to the rest. It'll be a long way to go. Okay. Now let's resume. Have to prepare yourself a bit, okay? Before we start on unclustered part. Okay. The hardest part to understand is about when we have unclustered that it's not alternative 1. When we have alternative 2 or 3, the index structure or index node will contain a smaller size of the data because it's not the whole data record anymore. So instead of having one page that could hold 10 data records. Now we can hold more than 10 data records because the index entry is, let's say, is only 10% size. So we have the same size of the page. If before we can hold 10 data records, hold 10 full data records. But if we only have 10% size, you think you can get more things into one page? Yes. It will be 10 times more, right? Yeah. So that's the whole big idea about when we have index structure that is secondary index. We will be able to contain stuff more into one page than before. But how many more? You should be able to understand those. And when we do the scanning, how much time it would take you to scan all the data entries, the index entries page, and each one, if we have to get the actual data record, you have to go to another indirection. You have to go to data records in the next step. Versus if you use alternative one, you get to the actual data record right there. But in index, you have to go to index first. And once you know where it is, the index will point you to the actual data record later. Okay. So before we do that, that's why I have empty page for you here. Okay, let's review some of the important things before we go on. Okay, let's review. This is important. R is number of maximum. This is maximum data record. This is data records, not the index, okay? The actual data records with all the fields per page. Okay, I want to make this extra clear in the data file. Not data entry, okay? Otherwise, well, it's confusing later. Okay, R is number of maximum data records, full data records per page in the data file, not the data entry. Okay, now we talk about data entry. We assume that the size of data entry is 10% in the assumption page, okay? So data entry, of course, it is smaller in size. So depending on how small it is, it could be like data entry is 10% size, it could be 20% size, 50% size, whatever, depending on how large the original file would be, okay? So originally, let's say you can keep R records in one page. In one page. Okay, so that's a definition of R, right? You can keep R data records in one page. But if data entry size is 10%, what does it mean? That means one page can hold more. How many more? 10 times more, right? 10 times more entries. So instead of holding R, I can now hold 10R, right? Right? Thinking about the fixed size page. Originally, I can hold R records. But now, instead of holding R records, I want to hold 10% of R. Because I don't want to hold the whole, I don't want to put the whole data records in there anymore. I just want to put some data entry, the index part, which only costs you 10% size. That means I can put more stuff in there because I put smaller items in there. And how many more? Since each one is only 10% of the original size, so I can hold 10 times more, which is 10R. Okay, now let's say if data entry size is 20%. That means one page can hold how many times more? 5 times more entries. So that would be 5R. So it depends on the data entry size. That assumption would be 10% or 20% or whatever percent. If it's 100% size, well, that's R, right? Okay. So that's about R. Now we have two things to talk about. We have the tree and we have hash. Okay. First thing, for tree, we have 67 occupancy rate as our assumption. And we already talked about that. That would contribute to 1.5 V pages. Okay. Now, if the data entry size is 10%, that means 10% of 1.5 B page will be 0.15 B page total. So this will be number of leaf page of the index. Does it make sense? Yes. Because originally we talked about 1.5 B pages. But if those 1.5 B pages is not used for holding the full data records anymore, I want to put only the index part, which is only 10% size. So instead of having to take care of 1.5 B page, it's only 10% of that, which is 1.15 B pages. That's it. Okay, so you see that the index could just be a small portion of the storage. Okay, now if you want to find out how many data entries per page that you could hold, okay, since number of data entries per page, well, we have to make sure that we still stick with 67% occupancy rate. So instead of holding R, I can only allow to hold 2/3 R or 67%. So 2/3 R. So 10% of that. So X will be 2/3 R times 10. So that's just that. Oops, sorry. This is what I'm trying to get you at. So instead of 10R or 5R, I want to find out how many R's that does it allow. So here, this is about 6.7 R. There. Yeah. If it's just 10% flat without occupancy rates, well, that would be easy, just like the top part, right? But now we have to take care of occupancy rate as well. So just put that into account. So instead of 10R, I cannot hold 10R anymore, right? Because if it's just 10%, that's just 10R, very easy. But now I cannot hold 10R. I can only hold 6.7R because I have to leave something empty for occupancy rate of 67%. Okay, Now for scanning. For scanning, if I have to read every single page, that means I have to fetch every data page from every data entry in every page, in every leaf page. So let's say how much time I will need. Total, I have 0.15 B pages, and each page is holding 20 over 3 R times D. And overall, that's BRD. This is a total number of time needed if you want to scan every single thing, fetch every single data page from every data entry in every single leaf page. Okay. Because think about compare, this is important because if you back to the tree, the clustered and unclustered part. If it's clustered, let's say a few entries from the index will probably correspond to the same data page because it has the same ordering. But for unclustered, like this one, unclustered, one index entry could point to page 7. The next index entry could point to page 1. The next one could point to page 20. The other one could point to page 25, whatever. So even though the items in the same index page, but since it's sorted in there, it has different ordering in terms of data page. That's why one entry means one page read, one entry, one page read. That's very expensive. Okay. So that's BRD. BRD, that's very expensive. This is what I want to show you how we get to that expensive part. And the same way happen with hash when it is unclustered also. For hash, we assume that we have 80% occupancy. So that's 1.25 B pages. And the same idea. For data entry size, let's assume that it's 10%. So 10% of 1.25 B, that's 0.125 B. That's number of buckets of index. So if you want to look at number of data entries per bucket, this is per bucket or per page, this is a thing. So if we want to take care of 80% occupancy, that's 8R. So instead of holding 10R as usual, we can only take 8R. But it's better than 6.7R because occupancy rate is 80%, not 67%. And here, if you have to fetch every data page from every data entry in every bucket. So that would take 0.125 B times 8R times D. And that's also BRD. You see that it's very expensive there. Okay. Actually, I don't have to explain all of you these things, but well, you may have questions. Why? How we get to BRD? Because here, if you look at the cost of scanning, we have BRD plus 0.15 BD. Like where? How we get to BRD? Yeah, that's how we get to BRD. Okay. All right. So let's take a look at how we get to this thing. If you want to scan everything, okay, let's okay. Let's talk about if we have to use the index structure, V plus tree structure, to get to every single item. Okay. We have to scan leaf page in the index. Okay. Have to understand that leaf page in the index right now has no data records. It's just the index part. It only contains search key value. For example, if you only take age, this age only, that's why it's very small in size. Or if you want to take only names or only like whatever as a search key. So if I have to scan everything, that means I have to scan all the leaf pages in the index. That only contains the search key. If you want to the actual data record, you have to follow the pointers to the actual data record later. And one pointer that points to data record, it will point to one big data page. And then you get that data page and then you find the items there. And when you scan to the next item in the leaf page, that could correspond to another different page that you have to read there. So if you want to look at leaf page in the index, how many leaf page do I have? Well, based on this thing, it will be 0.15 the right number of leaf page of the index right here. So I have a total of 0.15 B pages of the index part times D. That's the time it takes for me to read every single leaf page of the index. But now the most important part or most expensive part would be for each data entry. We have to fetch the real data record from data file. And that would take BRD that we did earlier. So overall, that's why we get this plus 0.15 BD there, scanning. So you could see that it takes much, much, much longer time to scan using the index structure, comparing with the typical scan of BD or 1.5 BD, right? So in general, even though you have the index structure, sometimes EVMS is intelligent enough for you. Sometimes it's just to skip the index structure. If they know that, oh, I have to scan the whole table anyway. So it probably would not use the index structure because it takes longer, much, much longer time. So that's for scanning. Now for equality search. Okay, how do we get to the equality search there of D plus log base of 0.15? Okay, first equality search, we have to start from the root node of the index structure, B plus tree. And then we have to locate the page. Of data entry. Let's say I want to find page 17 there. I put 17 in the root node, and then it will direct me to the leaf page of the index entry that 17 should be there. Okay. So locate that page of data entry. That could take me how much time? It will be log of, right now, when we talk about index entry or data entry, we will not talk about 1.5 B page anymore because it's only 10% size. So it will be 0.15 B pages. Base F. F is fan out or number of pointers per node times D. This will get me to the leaf page of the index part. And then let's say I want to find the record of person with age 17. I will follow the pointers from there to the actual data record. Fetch data record from file, from data file. And when I fetch, even though I want to fetch one data record, I cannot do that. I have to take the whole page. I have to bring out the whole page. So that would take me D time to read that one page. So that would give me D plus log of 0.15 B base F times D. Okay. Questions? Okay, next would be the range search. Range search, we start off with something the same as equality search. We have to locate the first item, right? Locate the page of data entry. Of the first item to search, okay? So that would take me the same time, 0.15 B. Now I get the starting point, and then the rest, depending on how many matches I have. But this is the main difference, very, very important difference. Number of match records. Not the match pages anymore. Because in the previous, in the cluster version, this match means match pages because things would stay in the same page for consecutive items. But it's not true for unclustered index anymore. Consecutive items in index structure would not be consecutive in the real data records anymore because they're different ordering. Okay, so one records mean one page. One records mean one page. So if I have 3 extra records to match, that means I have to read 3 extra pages. If I have 10 more records to match, that means I have to read 10 extra pages. This is the main difference of unclustered versus clustered index, because one records mean one page, one records mean one page because they're not in consecutive order. So depending on number of match data records. And for each of them match record, that will take you D time for each of them. Okay. So here, if I want to make it more exact, match records times D. But here, this is match pages times D. Well, that's the main difference. Okay, the next one for insert. Okay, pay attention on this one because there are many extra steps that we need to do for unclustered tree index. First, if you want to insert something into the existing tree, how or where should I insert something into? First thing that I could do, because this is a heap file, right? So I know that if I have to take care of a heap file, I can just insert the same way as heap because it's heap, right? So I can insert at EOF. Insert new record in heap file at EOF. But to insert something at EOF, there are many things that's going on. First, I have to fetch the page, the empty page, or the last page that I could insert something. So that would be D time, fetch the page, and then I insert data record. And then I write back. So that's another D time to write back. So overall, to insert a new data record in a heap file at EOF, that takes me 2D time, which is the same as heap right there, right? But this is far from finished because this is done in the heap level, heap file level only. But we have index structure, the whole index structure to take care of, right? I just inserted new stuff in there. I have to make sure that the index know what I did, like in terms of insertion. So I need to modify the index accordingly. Modify index. How do I modify the index? I have to insert the data entry into the index as well. Every time I insert new data record, I have to take that search key and I insert it into the index. Insert new data entry in the index. But how do I insert that data entry into the index? I have to find the correct leaf page so that I can insert them into the right position. Right. So I need to find the correct leaf page. To insert. That would take me the equality search time, right? So D times log 0.15p. Okay, this is just find the leaf page in the index part. And then I can add new data entry in there. And then once I'm done, I just have to write back the modified page. This is a leaf page. So write back that one page, that's D time. So if you count total, we have 2D plus 1D, that's 3D already, plus D times log 0.15 B base F. So that's what we have right there. Okay. So just you know that 3D doesn't come from the same part. The first 2D comes from insertion in the heap file, and the other D comes from the write back part of the index structure. Okay. Now the last part is a deletion. To delete something, yeah. We cannot take things from heap file right away because, well, we don't know where it is. Everything is random. So we need to use the index structure first to find out where to delete stuff, which is in reverse of insert. Insert, we know exactly where to insert because we insert at the end of file, right? We can insert right at heap file. Well, when we delete, we cannot do that. Okay, so to delete, we have to locate the item. We cannot get to the item yet. We have to just go to the leaf page of the data entry, the index part. Locate the data entry. And that could take you the time log F. Just that. For this part, we get to the leaf page of the data entry, the index part. And now we can fetch the data record. Real data record from here. But you have to understand that when I say fetch real data record, we have to take the whole page. We have to read the whole page. You cannot just read that record out. So that whole page costs you D time to fetch. So that whole page that contains that data record is there. Now you can delete. Delete record from heap. Delete takes you, well, CPU time, so we don't really count. The important part is to write back. Write back to heap. So that takes you D time to write back. Well, we're not done. Because if we're done, that means we haven't updated our data entry yet. Okay. So we also have to delete item from data entry or index part. And then write back. Data entry page or the index part. That's also another D time. Okay. So overall, we have 3 Ds again. And then one equality search. Okay. So here you look search plus 2D. It's actually the same thing because here we have 1D right here. This is a search. This is 1D plus log plus 2D. That's total of 3 plus log. That's the same thing. All right. Okay. Let's recap again for the delete. To be able to delete, you have to use the index structure to find out where the item is located. So first, you go to locate the data entry in the leaf node, and that takes you the log time. And once you get to that page, you have to fetch the actual data record, the whole page there from heap. So that's take you one page read. That's D time. And then that page in the heap file is on memory. You can delete the actual data record from heap file and then write that page back. That's another D time. And then you have to modify the data entry, the index part. You can delete the item from index entry and then write back that index entry page. That's another D time. So overall, that's 3D plus log of 0.15 BF. That's for 3. Okay. All right. Now the last 5 things should be easier now because, well, unclustered both heap and tree has very similar operations. First one, scanning the hash index and unclustered index. First, we have to scan the not the leaf page, scan the bucket. In the index file. Okay, now how many buckets do we have? So based on things that we did earlier, that we started off with 1.25 B pages for 50% occupancy rate, but since it's 10% size, so it's 0.125 BD. That's to scan every single buckets, every bucket in the index part. And then for each data entry in their bucket, fetch the real data record. From heap file. That's BRD that we did the calculation earlier. Okay. So overall, that's BRD plus 0.125 BD. The same situation happens with unclustered tree index, that if you want to do the full scan of the database and you have unclustered index, you are better off without having or you're better off not using index structure at all. You just scan everything sequentially. That's going to be much faster than using the index. Okay, now the next one. This is the highlight of the hash. Okay, you have to enjoy this cell so much. That equality search, because we know that hash is good for equality search. And this is the only thing that it's good for, mostly. Okay, so let's say if you want to do equality search using hash function. First, you have to locate the bucket of data entry. To locate, it takes you, well, one constant time, because that's what hash function is for. And then we can fetch or to read the page. Read the bucket. Right. That's the time. Make sure that you separate this thing to locate that's applying the hash function. It gives you some numbers, some value, but you have to fetch that bucket to read that bucket onto the main. And then that's only the index part. But if you want to take the whole data record, you also have to fetch the real data from heap file. But that's only one page though. That's also D page. So overall, that takes you only 2D. to get to your equality search data. Okay, so comparing to others in this column, equality search, 2Ds, much better than others. Okay. All right. Now range search. Okay, if you want to do range search, first you locate the data entry, the bucket, and you need to read that. Locate, that takes you 1, and then read takes you D, that's D time. And then for each of the match record, each of the match records, you have to multiply by D. And then you have to add them up together. Okay. So actually BD here is not coming from this part. Because, well, to just get one thing out, that's actually 2D, right? But you have to do that for every single match record. Well, if you have a lot of match records, that would take you a long time. So BD here, this is the cost that did not use the index structure at all. Actually, BD comes from here. Just scan the whole heap file. Scan the whole heap file. Well, actually, well, the same thing here, the range search there. Okay. It's actually the BMS is intelligent enough. When it tries to do something that it knows that if they have to follow through the whole index structure and it takes much longer time, it usually skipped it for you. And sometimes it will, let's say if you try to do range search using hash, sometimes it just override your command and say, oh, I'm going to use tree for you. Yeah. Okay. So here, range search using hash is bad. So most of the time, we just do not use the index or maybe use other type of index instead of the hash. Okay. Now let's take a look at insertion. Insertion is interesting. Well, I get 4D right there. Okay. First, the operations is very similar to unclustered tree index, that we can insert things at EOF. Okay. So we could insert new. Yes. Previous slide there. So. Yeah. Oh, here, like if for BD right here, that means if I don't use the index at all, that would be the cost of scanning the whole thing to find the range search. But if I have to use, if I force myself to use index structure, this is what it will cost. First thing, I have to locate the bucket, use a hash function to locate where it is, and then I read that bucket, the index part, that's D time. And then for that particular D item and the match, let's say I want to find 15 to 20. The first one I find 15. So 15, I have to read that D, this this D, that's 15. And then I have to fetch the actual data record. That's another D. Okay. And then 16, I have to repeat this thing over. 16, I have to find 16 and then see how many data records it matches to. And then I have to multiply by D, and then I repeat. So if it's not a lot, it's not that bad. But if the match records is a lot, so it could cost you a lot. So if I have to take the total, right? So it would be so depending on for each time it will be 2D, depending on how many times it takes. So you multiply by 2Ds. Because each equality search takes you 2D time. So depending on how many records it has a match, so you multiply by 2D. Yeah. Okay. Now for insertion, we can insert new data record in heap file at EOF. Okay. And that will means that I need to fetch the page, fetch an empty page to insert. That takes me D time, and then I can insert, and then I have to rewrite. That's D time. Okay, so this part, it's done in the heap file. But in the index part, I have to take care of the index part as well. So to insert, I have to locate the bucket of index. That takes me one constant time, and then I have to read the bucket. That's take me D time, and then I have to add new data entry into that bucket, and then I have to write back the bucket page. That's also D times. So total, that's 4D. Okay, the last one is delete. So to delete, okay, to delete, first I have to locate the data entry and read the buckets. That's D time. And then I have to fetch the real data record. From heap file. That's also another D time. Okay. And then what? Now I have the real data from heap file already. I could delete. And I could delete the data entry. And then I have to write back a lot of things. Write back, modify, bucket. Both for index and data file. Because we have the the bucket or the page that we read from the heat file and the one in the index part. So for the index, that's D time. For the data file, that's another D time. So overall, it's also 2D. The search is equality search 2D right there. So that's 4D total. Okay. All right. So I know it's a lot to get into your nerve today, but we have a few weeks to try to understand this thing. If you have questions afterwards, just you can come talk to me. All right. Now we still have other things to cover. Yeah. Now, why do we have to learn about indexing? Well, this is from like all the seniors or whoever that alumni who actually work at the on all the industries. It said one of the important things that they want everybody to learn about would be indexing, because they have to really understand, because getting the answer is not the only requirement. They want to do it fast, and you have to be able to speed things up for them somehow. And if you pick the wrong index, you pick the wrong attributes to do the index, it actually could slow things down. Or if you pick the wrong structure, that could actually still slow things down also. Okay, so to be able to pick the right ones, you have to understand the workload properly, like which relations we're talking about, which attributes are we talking about in the queries? Is it in the where clause and in the select from where, which one actually matters? And what are the attributes that are involved in the join and selection? And this is also very, how selective are these conditions? If you use the index structure, but the index is not selective enough, that it actually qualifies almost everybody. So why do you need index? The scanning would be, well, probably doing the same thing. Okay, but if it's very selective, meaning that out of a million data records, you use the index to look for one thing or two things, that you can actually gain a lot of benefit from index, right? Okay. All right, so selectivity is really important. And you have to understand what, because you already saw that insert, delete, updates, or like scanning, range search, equality search, they have different costs. So you have to think about, okay, you doing an index for what operation? And for that operation, which one would be the best choice for you? Okay, so to make the decision, what index should we create? Should we have the hash or tree or clustered, unclustered? Which relations? You don't have to build index on everything. You're not Google. Google does that, okay? Because they expect people to ask on every single thing. So they actually had largest storage on story index structure, because they index everything. Yeah, but you're not Google. So in your tables, relations, whatever, you just pick the ones that really matters to your queries. Okay, and like let's say if you have 10 fields, you may pick only one field as your search key, or maybe compose it like age and salary, just that. But for Google, they have to like the single attribute, 2 attributes, 3 attributes, 5 attributes, 10 attributes. They have to do everything because they expect people to search on everything. Okay. So to make a choice for indices, usually we will consider most important queries by, well, you think about frequency, usually like which queries you do the most, and if you make that index for that particular queries, it will be helpful and make things faster for you. Because every time you create an index, we always have a trade-off, because when you search for things, usually index will make search faster, but you have to update things. So update to be slower, because you see every time you insert something, you have to update the index. You delete something, you have to update the index. So update to be much slower, and then you have to incur the disk space, because every time you create index, that's another storage that you have to, like, it's extra structure that you have to create. So if you're low on disk space, you have to think about, okay, well, all the index needs some space too. And if you over index or index everything, but that table got updated very frequently, that's really bad. Like have lots of insertion, lots of deletion, and then you have 50 index involved. So every time you update something, you have to update all the index involved. That's really bad. Like just think about, let's say you have Library of Congress, you have lots of books, like million books, and then you add one book there. That's bad. Oh, if it's one book, that's not that bad, but you have to update all the authors index, ISBN index, keyword index, all the index you have by adding one new book. If you add like 1,000 books every day, that means you have to update everything all the time. So if you have too many index that are not relevant or not really important, that means you have to spend a lot of time doing a lot of updates. So that's a thing that you have to think about. So the guideline, rough guideline would be, look at the attributes in where clause, not the select, not the from. We look at the where clause first. Okay. So if it's exact match, do the hash. If it's range, you use tree. Okay. Yeah. If you do not know whether or not in the future you will have range search or not, go with tree. Because if you go with hash is really specific for equality search. Okay, and multi-attribute search key. Well, sometimes when we have a lot of conditions, so we may be able to use the index-only strategy. Like instead of having to read the real data record from file every time, we can just look at the index structure, and it's good enough to answer those queries without accessing the IO at all. Yeah, so that could be something to consider as well. We take a look at index-only strategy just a little bit. And if possible, try to choose index that benefit as many queries as possible, so that it's worth creating that index. Okay, now let's take a look at examples of some indices. For the first one, if you look at the query, I want to display the department number of employee whose age is greater than 40. Okay. So let's say I have employees table, and I want to list out only people whose age is more than 40, but not list the name, but list the department number that they're in. Okay. So should I create an index for this or not? Well, if I index on age, that means my employee table, well, I have age, right? And then I ordered things by age. So starting from, let's say 20, 22, 23, 23, 24, 25, whatever. And then when I get to people with 40 or more, 40, 41, 42, so that's the blob of people with age more than 40. And then I have to list out the DNO. Would that be fast enough? That I can use the index of age to go to block of people whose age is more than 40. And then after that, I can list out the DNO. Well, okay. It depends on how selective the condition is. Let's say if this company contain like 90% of people is older than 40. So using the index is probably not very helpful because it's not very selective. Maybe not using the index structure at all, and I just scan the whole file, and then like almost everybody is more than 40 already. Okay. And let's say I want the second theory. I want to list out the DNO and count. So this is what I want. Count. Group by DNO. So department number 1, number 2, number 3, number 4, and how many people whose age is more than 10. So let's say DNO department number 1, we have 20 people. Department number 2, we have 15 people. This got 17 people and so on. Okay. So here, if I have age as index, would that help? No, it's not helping at all, because think about if I order everybody by age, like starting from a lower age, like 20, 30, 40, whatever, and then I group by DNO. But within DNO 1, I have to count how many people whose age is more than 10. The ordering of age doesn't help, because within the same age, I have different DNOs, people in different DNOs. But I want to tally people in DNO 1 only. So I have to take DNO 1 from age 20, DNO 1 from age 21, DNO 1 from age 20. That's really costly, very expensive. So having index on age here doesn't really help. But if I do the index on DNO, that's probably be much, much, much better. Why? Because let's say if I order everybody by DNO, so I have DNO 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, and so on. So if I want to do DNO 1 and count, so I can just go directly to block of people whose DNO is 1, and then I can count them. Even though I do sequential search in there, it's not that bad. And count people in DNO 1, especially ages more than 10. So it's not selective. Most people would have age more than 10 anyway. And then you go to DNO 2, and then you count. That's probably be much, much better than index on age in this case. Right. Okay. And next one, I want to list out DNO of employee whose hobbies equals stamps. So here, if I index on hobbies, so I can go directly to stamps, and then I just get only people with stamp as hobby, and then I list out the DNO. Here. Okay, now here we could have composite search key. Now let's take a look at, in the middle there, we have data records sorted by name. So this is alternative 1 there. And then we have different types of secondary index. We have index on age alone, salary alone, age followed by salary, and salary followed by age. Okay, now let's take a look at okay, here, this is choice number 1, choice number 2, number 3, 4, and 5. Okay, now let's say if I have equality theories, like where age equals 20 and salary equals to 75. So 1, 2, 3, or 5, 1, 2, 3, 4, 5. Which option would be my best choice for indexing? This is equality only. Age equals 20 and salary equals to 75. Okay, think about it. How many think it's one? Choice one. One is age followed by salary. Who's in number two? Salary first, followed by age. Fit three, age alone. Four, salary alone. And five, my name. Well, not five because name is not relevant there, right? Okay, so 1, 2, 3, 4. If it's difficult for you, it will be difficult for you in the exams. Okay, so well, it should be you should understand this enough so that you can answer this type of question, especially for your project as well. At the end, you have to do some indexing for your tables as well. So here, if you look, it's either age or salary. Now the question is, should I do age alone or salary alone? No, right? Because if I do age alone, so I can get to people with age 20, but within people age 20, salary is not sorted. So if I have to get to salary 75 within people with age 20, if I have some type of sorting of salary, it would help. So the choice would come down to one or two, age first or salary first. So I would say you would pick choice one if age is more selective. More selective means that if I get smaller amount after I get to age 20. But if we have fewer records for salary equals to 75, so if salary is more selective, we'll pick number two. Because the faster that we could get down to the most selective part first, it will be more helpful. So one or two would be good. But if we have more information about selectivity of age or salary, we could pick it better. Now for range query, if we only do age equals 20 alone, if just that, we can just pick number three, right? But if we have the equality plus the range search, age equal 20 and salary greater than 10, well, we have to use composite ones, right? But we will use the one with equality first. So we would go with age first, followed by the range one. So age and salary, that would be choice one. If you pick choice two, it will be particularly bad. Why? Because if you pick number two, you have to go with salary first. So we go to salary more than 10, which is probably like almost everybody there. And then for each salary choice, you have to look for age equals 20, which should be scattered around the whole part there. So it would take more time. But if you pick the first one, it would direct you to age equals 20 alone. And within age equals 20, salary is sorted. So you can get to salary more than 10 really quickly. Okay. Okay. This is also very similar to the previous one. We index on age and salary. If we want age equals 30, salary equals 4,000. So equality would be good. So age salary or salary age would also be good enough. But if the condition is like range search, all range. So if we have age salary or salary age will be good. But if we have equality and range together, we will have to do equality first. Not this one. Okay. And here is the index only plan. The one that I told you that if we plan well enough, you can answer a lot of queries without having to reach out to the actual data file. Now, the first one, we want to list out the manager from department table where those department has more than one employee there. So what we could do is, instead of accessing table from department table and employee table, if we make the index on DNO of employee table, we don't have to access the employee table at all. We just list out department number that some employee is listed for. That means that if we have something in the employee table.dno, that means that department already has someone there. So that's all it needs, because they need to list out the manager of department where we have more than one employee entitled. So here we can just use this one, look at DNO for this part. But here, since we're not making index on department table, we still have to access the department from the department table. But at least here we can save some of the IOs by not having to access the employee table there. And very similar approach with DNO from employee and EID. So we can list out EID right away from this part, because we already have everything available in the index part. We have the DNO and the corresponding employee ID with that DNO. We don't have to access the actual data record there. We just check for this thing using this one. And then if it's qualify the conditions, we can just put this thing in there without having to access the full data record. And this one is really, the next one is very handy. If we list out, we have list of DNLs. So all the employees, and then we have DNO. So we have 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, like that. So if you want to list out the number of employees in each department, we can just count these numbers. We don't have to actually get to the actual data, because we just have to count how many. And this index will just be that. This number of department number for each employee. And if you just want to count, that's all it needs. So this is index only approach. And the same thing with here, we want minimum of salary. If we have the list of department number and salary for each employee, we can just use information from this to find the minimum or an average here even. You don't have to access the full data records, because these are the only thing that we want in the query already. Just the value of the salary, that should be good enough. So if you could, index only plan would be really helpful and make things much, much faster. Okay, now this one, assuming that you sort of understand how it works. So let's try to think about this thing. We have two choices, DNO age and age DNO. Which one is better for the left one? In the left part, we want to list out number of employee whose age equals 30 in each department. Okay. So what we want is, we want this DNO 1, 2, 3, and then count in department number 1, how many employee whose age is exactly 30? Let's say there are 3 people, this is 5 people, 2 people, and so on. This is what we want. Now, if you want something like this, should I index using choice 1 or choice 2? How many think it's 1? How many think it's 2? Let's see. If it's choice 1, let's see. Let me write it out so it's clear to you. If it's choice 1, we have DNO and we have age. So we have to list based on DNO first. So DNO 1 comes first, followed by DNO 2, followed by DNO 3. And within the same DNO, we sort by age. So maybe age 20, 22, 25, 35, 20, 30, 30, 35, 36, whatever. This is 1. Number 2, we have age and DNO. So we start with age 20, 20, 20, 21, 23, 22, 23, 25, 30, 30, 30, 35, 36, whatever. And then DNO, if we have the same age, we sort by DNO. So let's say DNO 1, DNO 2, DNO 2, 3, 5, 6, whatever. Let's say here you have 1, 1, 2, whatever. Okay. Now, if we want the left, this one, age equals 30. And I want to count how many. So if you pick number 1, that means I'm going to answer this first row. So I go to DNO 1, and then I count people with age 30, which is not bad because all of these are sorted. So I can direct to age 30 and then count. And then I move on to the DNO number 2. And then I go to age 30 and then I count, right? Okay, not bad. But if you think about option 2, option 2, I just go to age 30 right there. And then for those people whose age is 30, it's listed based on DNO. Which one would be better? 2. 2 is better because these are the only data that are involved in my answer. And that's it. No extra ones, right? Because everybody in age 30, I have to count according to their DNOs. So I count DNO 1 comes first, and then I get the number and then go to 2, 3, 4, 5. So that's the portion of the data that I have to look at would be this part. But if I go with number 1, the portion that I have to look at will be larger, right? Yeah. Okay, so for this one, I go with number 2. Now for the next one, the only difference would be this part, greater than 30. Well, this is looking very similar. Now DNO 1, 2, 3, and count people whose age is more than 30, not exactly 30. So which one would be better in this case? Okay, if I use 2, that means age more than 30. So I have to look at people from this point on, right? For age more than 30. And then I have to go to age 35, count how many DNO 1, and I have to tally everybody from all the age groups. That's bad, right? Pretty bad, because I have to go to age 35, DNO 1, age 36, DNO 1, age 37, 38, whatever. and grab all the DNO1, and then I have to come back and go for DNO2, DNO2, 2, 2, DNO3, bad, right? But if I use number one, so I go to DNO1 first, and then I go directly to people with age 35, and then I count. And then I go to DNO2, I get to people more than age 30, and then 3, and then so on. So in this case, I don't have to go back and forth. I just go in one pass, and then I can get to the answer quickly. So this would be number one. Okay. So maybe you go back home and review this thing again and see the difference. Why you pick this one over the other one. Okay. So, well, overall, that what we've done in the past two lectures would be like see the importance of having index in your database. And we have different types of index. We have hash-based index, we have sorted files with no index, we have heap file, no index, and we have tree-based index. Okay. And we have alternative 1, 2, and 3. You have to see all the difference of organization choices. And well, we have clustered index. We learned about clustered, unclustered, primary versus secondary, dense index, sparse index. All the differences will be in different point of view, but it actually reflects the performance of your index as well. So to be able to pick out the right choice of index and right structure for your database, you need to understand the workloads, you need to understand the queries, like the updates, how much updates or what type of updates you have, and all the overheads that could happen, like the time and the storage, and also the index only strategy. That's also very helpful. And also ordering of the fields in the composite index actually matters. Okay, so that's about the index. We have the exercise. Yes. Let's see. We have the exercises for you to do. Okay. I give you 1 week to do. Okay. Oops. We have only five problems, and this will be very similar to things that you would see in the final exam. It could be some multiple choices like this, given some with some tables there and some scenarios. If you want to do this and that, what type of queries would be the best? Okay, and like here, number 2, number 3, and here we need to do some calculation. Say here we have hash, but you see here that I changed the occupancy rate for hash from 80% to 67%. So now you know how to adjust to those things. And data entry size is 20%. And we need to find out how many data entries per page or per bucket in that hash index. And if you want to list all the data records, how much IO you need, things like that. And number 5, we have cluster B plus tree index using alternative 1. If occupancy rate is 25% and things like that. What is the average cost to find appropriate leaf page to insert a new record? Something like that. So there are different operations. So if you understand each operation that we talked about in the metrics there, it should be fine. Yes. 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 might be like I said. Something. Not sure. I haven't started making the exam yet, but I'd say it would be fair enough to have all types because we have SQL part as well. So you probably have to write some snippets, not a lot because I know it's a written exam. We used to have labs, so you had to use computer for like yeah, we have graders and all, but now we don't have the lab anymore. So we try to yeah, yeah, you have to be tested somehow, but you'll be allowed to take some cheat sheets there just to reduce down the yeah. Um, what do you think? Well, yeah, I would think so as well, because most of that stuff that we do in class, um we focus on relational database. So mostly on relational. But for at least NoSQL, you should know the conceptual part, like the difference or what it is and yeah, things like that. Yeah, but not the actual coding where you don't have to memorize the port number, things like that. Yeah. All right. So you will have 1 week to do this exercise. And then since we don't have Monday lecture, I will probably, what do I do? Well, I will post the solution to this exercise after next week. So if you have question or if you want me to explain more, I could like do the explanation and I put on the clips somewhere there or things like that. All right. So that'll be it for today. We see you like after Songkran in milestone 4. Yeah. So Monday we have the like online clips for one more lecture. Okay. Yeah. And for the groups that still have not really finalized your ER, whatever, you can come talk to me, right? Because otherwise you see each other in the milestone 4. That's yeah, there. All right.